Should I mute my PC? I mean,
don't think that your audio
my
is.
speaker.
Oh, yeah.
You said you're traveling, right? In a few weeks.
Yes. Great. All right, it's my pleasure to introduce Yu Tsunetoe. He's a Japanese Society for the Promotion of Science, or JSPS fellow here at the BHI. He earned his PhD in 2023 at Kyoto University under the mentorship of Shin Mineshige. Even before joining the EHT collaboration in the last year, Yu gained the attention of us EHT theorists because of his great work on polarization on EHT scales, using his very own GRRT code called Shako. At BHI, he's been working with Ramesh, making exciting predictions that you'll be seeing for what we'll be able to learn in the time domain and with good spatial resolution and dynamic range, things that are very relevant for NG-EHT impacts. So please take it away.
Okay, thank you for the introduction. And I'm Yu Tsunetoe, postdoc at BHI. So today I'm going to talk about some theoretical polarization images of black hole jet. So a composition of today's talk is as follows. After outlining the introduction of method about the images, I'll introduce the one main topic, which is about the horizon scale dynamics and extended jet images. That should be here. And also, if we have time, I will also talk about these works, which I mainly work in Japan. So I want to start with an introduction and methodology to predict the images of black hole and jet. So recently, as you saw, and maybe as you did, the EHT and other realistic observation have realized the direct imaging of supermassive black hole. The M87 star, and one of the main targets, is also correspond to the innermost region of the M87 jet, extended up to galactic kiloparsec scale, as shown in these images. And furthermore, the NGST and VEX Black Hole Explorer prospect the detection of the jet launching region, directly connecting with the photoning black hole shadow. So now, in which the plasma is thought to receive the energy from the spinning black hole and accelerating into the relativistic region. So this means we're now facing on the opportunity for investigating the most essential part of the magnetically driven jet from the black hole. So seizing this to seize this opportunity, we think of predicting the jet images on this scale to compare the upcoming observational images. To predict the image, firstly, we have to model the system of black hole accretion disk and jet by GLMHD simulation. In particular, the magnetically arrested disk or MAD models are sometimes often favored to reproduce the emission from around the black hole, which is characterized with a strong magnetic field, which affects the magnetic hydrodynamics around the black hole and leads to the large variability of plasma around the black hole. And here we also focus on the magnetic flux on the event horizon, 5EH, and defined with this equation on the box. And it characterizes the variability and madness of plasma around black hole and regarded as an important quantity in a series of GLMHD simulations. So to obtain the image, we perform GL radiative transfer calculation based on the GLMHD model. For this, I've developed a polarized GLRD called Shako since I was in graduate school. And in this code, it firstly determines the light ray path of photons by GL ray tracing method like this. And here we calculate the propagation equation of photon backwards from the observer's screen to black hole. And then once we determine the right path, we calculate radiative transfer equation, this equation with Stokes parameter IQU, and we forwards one black hole to the screen, referencing the GLMT data. And finally, we construct the image from the Stokes parameter on each pixel on the screen. So it's our methodology.
So what is lambda?
Lambda is a fine parameter of the photon trajectory. So far, we've outlined the method to obtain the images. So then we'll move on to the main topic about the relationship between horizon scale magnetic dynamics and the images of jet launching feature. Here we use MAD model described in Narayan 2022, in which the author surveyed the MAD model for different black hole spin values. Firstly, we here take a retrograde spinning black hole with A star equal minus 0.9, and use a data set covering duration of 5,000 TG, which is approximately 5 years for M87 star. And as shown in the bottom right, it shows the large variability and morphology of disk and jet are drastically changing over 1,000 TG scales. And using this GLMT data, I calculated the image at 86 gigahertz with shadow hold. And here we assume the inclination of 70 degrees. And the further, the image are also blurred with 40 microarc second circular Gaussian, bearing the actual angular resolution in mind. And the resultant images or movie is this. It also shows a large variability reflecting the MAD feature of the GLMT model. And here I pick up two snapshots from the dataset with a feed showing the truncated and broadened jet component. And in the bottom right, I also show the profile of magnetic flux over 5,000 TG, and the two vertical dashed lines correspond to the snapshot. And we here see the path of the moment. I mean the left side of the to each line, and find the big drop and rise of the in 5EH prior to the snapshot. So these are equal to the erupting and accumulating events. These drops and rise correspond to the eruption and accumulation of magnetic flux onto the black hole. So here, this feature leads us to the hypothesis that the drop and rise in 5EH can lead to the truncation and broadening of jet. Or more generally, the dynamical magnetic flux can affect the jet morphology on larger scale. So next, we verify this hypothesis. Here, we measure the total intensity flux density. I mean, the integrating the all image as is something like as if observed as one point source and show the profile. In addition to the jet width profile, we as shown by the green line, we measure the jet width at each Y on the image from 25 to 150 RG. It corresponds to up to 0.6 milliarc second in M87 stars.
Quick question. Does the truncation must depend on how you model the external environment, right? Okay, so how do you, what are the properties?
You mean the jet truncation? Yes, we modified the, I'll say, jet is truncated at the dynamic range of 10 to the 3, 1,000. So the outermost line is about 1,000 times dimmer than the peak. and I define the jet edge there.
Oh, but is it propagating into vacuum, or have you imposed
Right.
a sort of density floor in the simulation?
And so you,
The medium, like where is it,
uh,
the environment of the,
actually, a jet emission is more extended than the definition of the jet width here. But how say? So you dense. How you ask how to avoid the density floor?
No,
no, are you imposing a density floor? What are your conditions? What is the medium? Is there a medium into which the jet is expanding or no?
This is the standard torus simulation.
Hmm.
So the entire torus is in that black region,
Oh,
and the jet is coming out along the funnel.
Yeah, so we actually also how say not only jet but expanding jet. How say? It's also ambiguous whether it's jet or whether it's this. So, but here we define on the image we define the jet expands over the dynamic range of 10 to the 3.
Okay.
Actually, the plasma.
is it a quasi-spherical, the torus? What is the density distribution in the torus? What is the jet expanding?
Maybe we should do that later, because this is not his
It's not
work.
relevant. Okay.
This is the GRMHD simulation. It's absolutely standard simulation that everybody does.
Oh.
And it's the inner region, and you've got a confined jet, and at 86 gigahertz, U is finding that the radiation is dominated by the jet.
Yes, on the image we didn't truncate any. I would say
Okay.
we truncate. We consider all the pixel and calculate latitude concentration. So we in principle it's non-zero for
All of
all over more.
I see. Okay.
So so now, yeah, we plot the profile of the how say total flux density and jet width at each y, and at the same time we also plot the 5EH profile in the bottom, which is not the observable quantity, but we just directly obtained from the low GLMHD data. And comparing these profiles, we can see the how say the jet width profile is very similar to the 5EH with some time lag, as well as the total flux density profile. As we saw in the previous slide, the drop in 5EH is followed by the truncation there. Now drop and truncate, and rise and expanding. So yeah, we can see the strong connection between the magnetic flux on the event horizon and jet width on my extended region. So then.
So one question. That image and movie, are we looking at 17 degrees cubic angle? Okay, so when it goes to 150, it's actually 450 in the actual distance.
Yes, the projected with sine.
Yeah, which is about 1/3, yeah.
So yeah, actual GLMHD coordinate is how to say 3 times y is correspond to z in the GLMHD coordinate.
Good.
So then we'll evaluate the connection between the 5EH and jet width by correlation function analysis. The correlation function is given in the box equation, and we calculate each function and plot in this diagram. And at the same time, we also calculate the correlation between 5EH and the total intensity flux by the denoted by -1. And we can see that the 5EH and jet width show even stronger correlation of 0.5, but 0.8, more than the 5EH and the total flux correlation shown by it's about 0.6.
Sorry,
Can you remind me what 5EH is?
Okay,
What does
5
it stand for? What's the, you said it's something we can't really observe, but what is it? Oh, there you go. There you go.
5H is not unobservable,
But what is it?
is
right
not observable, but we can, it's directly calculated from GLM
now? But
simulation.
what quantity is it from us?
Okay,
You defined it in the previous slide.
I just didn't remember.
okay,
Oh, drop and rise of flux of
You have the
accumulated.
definition, right?
Yeah, okay, good. Okay, thank you.
yes, 5H is correspond to the magnetic strength of the magnetic field related into the event horizon.
Thank you.
And yeah, it's characterized the dynamics of the black hole. And yeah, overall, the 5VH and ZVH have strong correlation. And we also see the time lag. Time lag is correspond to the delta T peak, so it's peak position of each function. And this time lag are larger at outer jet. So it suggests the the jet width variation propagating with plasma motion from upstream to downstream side of the jet. As so, in this way, we saw the jet width very strongly indicate the dynamics of magnetic flux of the event horizon.
For the smaller peak on the left side,
This
should that be, no, for all the colors, it seems like there is a constant offset from the primary peak to the secondary peak. Is there kind of like a periodicity in the jet truncation and explosion?
Maybe, yeah.
Or
Yeah,
am I-
it looks like parallel shift, parallel, yeah, shifting parallel, but I didn't go in depth about this, but yeah, I think those maybe implying something, but basically we don't believe in the correlation point 2 or 3 so strong. So yeah, but yeah, maybe we can say something from this. I think it's also rising some more larger periodic cycle. Maybe it's imprinting some larger periodic cycle, more longer time scale.
How does this depend on your initial and final time values? Like, do you pick a period where the
Yes.
change in the flux is large? Or
I believe, we pick up the data from the data in the quasi steady state. So I will stable in the over 5,000. The typical.
I see.
Yeah, we try to pick up the typical 5,000 TG data.
Okay, thank you.
So here we introduce 2 examples of application, observation application in the opposite direction timeline. The first one is jet archaeology. That is, we can infer the dynamical history of black hole from the observation at larger scale, on larger scale. As a quick example, we can guess from the width variation in this orange region that 5VH was increasing, or in other words, the magnetic flux was accumulating onto the black hole before this initial point, 78,000. And yeah, so we can like this we can infer yes, we can know the path of the 5VH from the jet width image. And the second application is jet weather gas. If we know the 5H variation from, for example, the total flux or any other high energy flaring event, as like gamma or X-ray, we can forecast the upcoming change in the jet shape. So it's like a weather gas. And as shown by the light blue box, we can forecast the narrowing of the jet after the final time point, 83,000 each.
Is there like a propagation speed that the
Yes, I show the next
oh,
slide.
okay.
As shows the outer jet width shows larger delay. So we next use this. So here we think of another application regarding the jet acceleration profile. As we saw, the 5BH 5BH variation is transmitted to firstly to the total flux and to the jet width from up to downstream side. So focusing on this, we try to estimate the jet velocity profile from these two observable total flux and jet width. And we calculate the correlation between these two and plot the time gap delta T peak here. And it nicely converging into the line of V equals T, the speed of light, suggesting the persistent acceleration into the relativistic region. And we, at the same time, we also plot the low data profile from the GLMG, and it was shows consistent. We can see they are consistent with actual low data. So we can also expect to follow the jet acceleration profile, where total flux and jet width these two observable in future observation with higher angular resolution and higher sensitivity.
So you have to stop here.
Okay.
This is new. I haven't seen this
Yeah.
before, right?
I did it yesterday.
You did it yesterday. I believe it. But this looks pretty remarkable to me because those dots, they are coming from jet width, which is really a pattern velocity.
Yes,
Yes.
jet is also steering, so
Sharing, all sorts of things are happening. So the blue line is real velocity from the GRMHD, is the actual velocity of the plasma.
yes, but there is an uncertainty. Where we should pick up the velocity profile.
Yes.
But, so maybe it depends on but we now safely pick up from some broad region, I would say, with high sigma, where the large amount of emission was produced there.
Okay, but this is great. It means that the pattern
I
is
think
close to the actual velocity of the plasma. Amazing. Okay, sorry. Yeah, keep going.
it's kind of surprisingly in that it's average profile. So the jet velocity profile is also variable over over 5,000 PG. Nevertheless, we can reproduce the persistent profile over 1,000 PG. So we can salvage the jet acceleration profile from long term, like years long observations. Okay, so far we focused on the analysis and discussion for on retrograde S equal -0.9 case.
That's accurate. So it goes up to like 500 RG. Do you know what time frame that is for M87? 5 years.
Yes,
Oh, that's what that
5 years.
is. Okay.
Yes, 5,000 TZ correspond to 5 years in MD stable. I mean, for Sagittarius, it correspond to hours or days. It's roughly 1,000 times shorter, smaller scale. So, so we now confirm the connection between 5BH and jet width for S equal -0.9, the retrograde, fastly spinning retrograde, spinning black hole. So we also confirmed the qualitatively same results for these 5 spins, primary 0.9, primary 0.5, and non-spinning black hole. And as an example, we show the prograde fast spinning black hole on S equal 0.9 as a problem. And at the same time, we also calculate the statistical deviation for 5,000 PG for these five spin cases, and plotted it here. We also we here calculate the deviation of two quantities. One is a 5BH and one is a jet wave size, like 50 RG. There's a in middle of image, and it shows how say the jet wave deviation reproduce that the spin dependence of capital 5BH. We should note that this capital 5BH is a little different from the small normal 5BH we showed before. In that, the capital BH is not normalized by with the mass acquisition rate. But anyway, it's there how say consistently show the similar deviation to each other, larger for fast spinning retrograde spinning black hole. So yeah, we may expect to determine the spin from long-term, years-long observations of the jet wave in the jet launching picture.
Would you say why you chose the capital 5 here? Like, is the mass
normal small the small normal 5BH that doesn't show their tendency like this. It's a so the 5BH is unnormalized magnetic flux, and it's strongly more strongly reflect the capital 5BH is more strongly imprinted in the jet wave, and even stronger correlation, and it also determines the deviation of jet wave at each altitude.
Okay. So if there's zero spin, what's causing the jet?
It's good point. So so go next.
Yeah, no agenda.
No agenda. Okay, I didn't say it, but non-spinning case, we consider the jet width at 10 RG. It's clearly detectable on this image, and obtain the similar energy. So it's a little different from the spinning case. And okay, let's show the spin dependence time average image. And these are averaged total intensity image over 5,000 feet. And at a glance, you notice the non-spinning black hole doesn't produce the extended jet image. This is because of their weak acceleration and lower magnetization in the final region. So we can say by nature it doesn't have outstanding jet, even in geometry data. So yeah, I want to say it's not the apparent effect of radiative transfer, but actually jet is outside for non-spinning case.
So in the plot that you had before, the least variable one was the non-spin, and the second was the retrograde high spin, or the prograde high spin. Was that the plot wasn't monotonic? It like had a turnover. It looked like
Previous slide.
Yes.
previous slide, yeah.
Yes, it's a turnaround of non-spinning case, but retrograde overall retrograde spin case more variable.
Prograde.
Yes. And yeah, so it was a
Hey, Counselor, can you go back to that slide again? So I keep asking myself, what's causing the phi VH? Is this like an accretion process?
that's
And if so, like, the spin is governing the accretion, and that's why the phi VH is very low for zero spin.
Yeah, that's very good question. I was frequently asked like that. So, and I have no specific answer. It's a consequence of several factors, including like the in Narayan 2022, the different black hole spins shows different jet disk morphology. So it's a how to say? Yeah, overall the high they show the higher 5EH shows more wider jet. So it must I believe it must be the some consequence of geometrical effect around black hole. And yeah, black hole spin is imprinted in some way in this deviation, but I have no specific answer.
Is the dramatic difference between minus 0.9 and plus 0.9 because one is prograde, one is retrograde? Why are they so asymmetric?
I have no.
Nobody knows. These are, in some sense, experimental results. You run a simulation, pull out some statistics, looked interesting, you make a picture and you publish it, but there's no explanation. But, yeah, I'm sure Charles knows why it's happening, but yeah.
I can't say.
You know what you can say?
Oh, really?
He knows, but he
I
cannot
think
say, yeah.
it's not well understood yet. It's interesting.
Yeah,
Yeah.
at least we empirically obtain tendencies, and yeah, it can be some trace of for spin damage.
Yeah, the thing I was wondering is that if this 0.9 prograde, like, is it lower than the 0.5? It just like, is it that normal that like a statistical, like if you ran the simulation, would you go up or?
It's not very precise.
So this is a fractional deviation. And my understanding was that for maths, the phi tends to vary gently with spin. And so the absolute variation is also changing quite a lot here. Is that correct?
I think it doesn't then always follow the how to say jet strength and how to say the jet strength and the deviation 5EH and not necessarily correlate.
Well, sure, and I guess the thing that I'm maybe getting hung up on is that the jet width I would expect to vary in an absolute sense with respect to spin, and to some great degree. I mean, evidently, it's actually not changing that much, but whereas 5EH I thought tended to pile up at a pretty stable value regardless of spin. I understand there are trends there, but anyway, reducing them both to a fractional variation sort of suggests that they are trending similarly. Because otherwise, if you had some sort of global, huge variation of these parameters as you change spin, then I guess I would expect the fractional variation to be sort of very sensitive to prograde versus retrograde, maybe weakly sensitive to fractional spin, or not fractional, to just spin period. But evidently that's not the case. I think maybe I'm just failing to wrap my head around it. But do you see a huge difference in these models in 5EH across spin without looking at deviation? Just typical sort of mean 5EH.
Mean 5EH. I mean, if you mean the absolute value.
Yeah.
Average for the time trend in 2022. It's the peak at point. Average program 0.5.
Right, but so I don't remember the results of the paper offhand, but wasn't this a difference of 35%? Am I misremembering? Huge. What is it?
I think it's more like 30%.
30%.
Yeah.
Really? Oh my gosh. Okay, that is way bigger than I would have. Yeah. Okay, thank you.
Guys, people have been tracking proper motions in the M87 jet for many years. Is this consistent with that? I seem to remember that things are relatively slow, close to the core, and then speed up as you go out.
You mean here? How say? It's yeah. In the jet waves also propagate slowly at first and gradually accelerating.
I guess it sort of depends on where the transition happens, doesn't it? Because it goes up to 450 RV, right?
Yeah, this is deprojected 450, but I think those results are much larger.
So this is
So it's after the projection.
Yeah.
It's actually actual coordinate in geometry.
You are thinking of the Walker movie? Yeah, where, things are moving. Very good question. One should look, but that's way out beyond. This is all close to the black hole. This is for NGEHT and BEX of interest. But yeah, simulations can't be trusted further out. And that's where all the previous data are available.
Actually, they had some images in the first slide, the different observations. Is there one of those observations that correspond to these length scales?
You mean the first
Yeah,
observation?
that way, yeah.
Now we consider, I think, this scale.
Okay, okay.
But are you already seeing V equals C? Is that what I'm understanding from that plot?
Yes, around there. Not equal, but I mean, in the order of point, I think 90%.
So it's already
Relatively.
extremely fast.
Yeah.
There's no room to accelerate much more.
90%, 99%.
Big difference. In gamma.
That's true.
Okay, so we now saw the non-spinning no jet. And we also see the fastly spinning case, the 0.9 spins, the right and left, more symmetrical jet than the moderate spin case, than 0.5 and minus 0.5 and 0.5. So we consider about this next. So here we introduce the image asymmetry by the relativistic beaming effect. As shown in the bottom right diagram, the 5 spin cases give more helical or the 0.5 spin cases show more toroidal plasma Barak motion than the 0.9 the two plus minus 0.9 spin cases. So this helix angle is small, it's both in the ballpark of 5 to 20 degrees, but now close to the viewing angle of observer, 70 degrees. And so they give a large gap between beamed and debeamed side of jet, in which the plasma bag approaching to and receding from the observer, respectively, and give rise to such an asymmetric jet edge. Now the right side is being on left side being plasma moving like. That's why the model spin and shows more asymmetric feature.
Could this also just be precession?
I think I didn't check about the precision was how say the variation of position angle share, because it's now largely biased with this just this beaming effect, and it's a little difficult to persistently define the jet's position angle. But so yeah, we now focus on just the width of the jet. I mean, it doesn't offset so largely. How say the jet overall constraint is being colored region.
Maybe I'm misreading the contours here, but I guess are the contouring schemes the same in the two images? Because it looks to me that if these are log contours, you get maybe 2 orders of magnitude drop between these 2 points.
Yeah,
and that seems
on
to
these
improve
images,
both images.
the peak of color and line contour is the same, and these two cases roughly gives the same total intensity on average.
Well, I guess the thing that I'm getting stuck on is it looks like there's a 2-degree difference in pitch angle at the, is this the deep projected distance? Yeah. So distance is 400 m. So on the sort of upper end of the image,
Yes.
there's a 2-degree difference in the velocity pitch angle. That seems, quite small to me, and I would guess that the ratio between sort of the right side and the left side is somewhat comparable in the two images, and maybe what's drawing the eye is just an overall difference in brightness at a large distance.
The both images generally show the more symmetrical emission in the outer side.
Sure.
It's consistent with these profiles. Actually, the helical, the plasma bulk motion gets more voidal in the outer region. But this 1 or 2 degree makes large difference in the case of
I see. Okay.
it's always case in the relativistic region. 1 or 2 degree makes big difference.
That's fair, yeah.
And I believe the gap is kind of bigger than the, I'll say, in the upstream side. And that's why it shows gives a more symmetric emission around here.
Okay, thanks.
So next, we want before proceeding with the discussion of polarization image, I want to review the polarization components from relativistic shell. So the synchrotron polarization produce a strong insight the configuration of magnetic field. Firstly, the linear polarization or LP vector indicates the direction of magnetic field projected onto the sky plane, as shown this. And it's, I'll say, the synchrotron polarization, the linear polarization component is dominant. It's about gives 80% polarized or linearly polarized. And secondly is the circular polarization, CP component, also gives a polarity of the magnetic field. That is the CP component implies whether the magnetic field line is aligned or anti-aligned to the line of sight. But basically, the circular polarization is weaker than the linear polarization in the ballpark of 1%. So by watching the LP and CP images, we can expect to survey the magnetic field configuration on the black hole and jet. But we should have to pay attention to the relativistic effect in the plasma bulk. These two Doppler beaming aberration. As shown in this picture, the radiation from the radiation in the relativistic plasma are concentrated into the direction of motion like this, and they are also blue shifted. So this is important in the implication of polarization in that the angular relation between magnetic field and the photon propagation vector can be modified in this plasmaless plane. So yeah, we should note these effects in interpretation of polarization in relativistic case. So now we'll move on to the time average LP maps for spinning black hole case, spinning black hole cases. And here, the color contrast shows the LP fraction and fixed overflowed fixed LP vector in EVPA, and the line control is the total intensity intensity distribution. And now we're more we can see the asymmetrical vector pattern commonly for the post or the post spin. So that is the vector shows the LP vector are horizontal in beamed right side and debeamed in the vertical in the debeamed left side. So we consider about this in the next slide. And on the basis of relativistic aberration effect. Here, firstly, we show some hypothetical image turning of the relativistic effect in the bottom left. And we can see the symmetrical pattern. Because now we see the helical magnetic field from Besson-like viewing above. Then, so the magnetic field shows projected magnetic field line is like this, and like I'll say it curl up around the jet wave and showing symmetrical epidemic pattern. So this is a non-relativistic case. Yes, this is a vector pattern is a non-relativistic case.
You one second, sorry.
Okay.
So in this, you have set the plasma velocity to be the Zamming velocity.
Yes,
And you're looking
put
down
the plasma at rest, almost at rest.
in the Zamming field. And you're looking down the pole.
Yes,
On
70
the
degrees.
exponential.
It's also the same.
Oh.
before.
I see.
So now the photon propagation vector is equal to the plasma left frame. Photon propagation vector are the same in the lava flame and the plasma left frame. So there's no aberration yet.
Do you have any intuition why the polarization peaks in the middle?
And it's more the most aligned.
Yeah, I guess my intuition is that like if you take like a cup, like
Yeah,
like you
like
take
this. And now loading up some low button.
like if you take
but-
like a transparent cup, normally the edges
Yes.
are where you see most of the optical interactions and not so much the middle. So I'm like
So you mean where?
if you take a cup, like a transparent cup, it's the opposite because it's not emitting light, it's absorbing light, but most of the absorption happens on the edge of the cup. Like when you take a transparent cup, because there's just like a longer path length for the light.
And it's actually now the jet has a three leads.
Yeah.
In negative fraction. One is as you said, it's come from the S, the most most aligned vector, and the middle one corresponds to the foreground and background emission.
Oh,
And in this case, it's aligned.
I see the polarization is a lot. I see it's like in the direct line of sight.
It never decay.
Okay.
But the intermediate region is not necessary order, and the polarization components here cancel out with each other.
Okay.
And give a smaller flash.
So that's a beautiful picture, and I love these results. These are so cool.
Thank you. You mean
So
this?
Just.
Yeah.
Right. So quick question, you've drawn this with the opening angle, not including the observer. Is that definitely the case? Have you measured the opening angle?
I couldn't get it.
So you've shown in your cartoon, which I love, that the opening angle of the jet does not include the observer. So you're looking from the outside in.
No, outside.
That's right. So have you confirmed
a-
in the simulations that that's true? Have you measured the opening angle of the jet?
It will be in this case now plasma is at least either way.
Sure. I think move on. Never mind.
Okay. So here I include the relativistic plasma back motion, and so as I said, so we here consider the more realistic image with the plasma back motion in the relativistic region, and the radiation in this case, the radiation point at larger angle, like this, by the aberration. So it's following, like this picture, the helical magnetic field projected more distorted shape on the screen, and it gives the more asymmetric pattern like this and this, and that's why, and so it's imprints the helicity of magnetic field, and the helicity comes from the flame dragging field by black hole gently. So we can also expect to survey the black hole methods from these asymmetric polarization. Can it be answer to your question?
I don't have any further questions. I'm just like.
Okay, it's also depends on the relation between bulk motion and inclination. more smaller inclination angle, it also gives a symmetric pattern, even with a relativistic. Or, yes, that.
So is the bulk motion consistent with the black hole spin or the fluid, the fluid velocity?
Yes, in now the helicity of black hole is like this, The spin now black hole spinning like this with the axis is right-handed spinning black hole, and it's in the spin imprinted in the magnetic field, and
So it just moves. It moves it in the direction of the black. Like the black hole is what's controlling the motion, not the initial fluid direction.
You mean about the prograd and the difference in prograd and retrograde?
Yeah.
It's how say in the jet, it is the same for both cases. I'll say, as we saw in the total intensity image, the both case shows beam in the image overall brighter than brighter in the light side. So yeah.
So the spin axis is pointing in the same direction. All
Yes, as bright. Yes, it also the same helicity as the black hole spin, not the disk.
Yeah.
So, and next we move on to the average CP images. So here, the positive and the negative CP components correspond to right-handed and left-handed circular polarization. And we can see the image shows some bipolar CP pattern with the opposite sign in the two sides of the jet, like here, positive in the light and negative in the light. It's the same for retrograde. So we discussed these CP in the basis of relativistic effects. As mentioned previously, the CP component imprints the polarity of the magnetic field and is proportional to K dot B in the plasma less flame. So now we see the, as we see the discussion of LP vector, now we see the helical magnetic field from the large inclination P. So it gives the positive CP in the left side and negative CP in the right side, as shown in the image. Does it make sense so far? Yes. Now, so in this case, we have the magnetic field like this. So it's aligned with the line of sight in the left side and anti-aligned in the right side. So we obtain the bipolar CP image. And we also plot the helical pitch angle of magnetic field for two different black hole spin here. And we can see that the higher black hole spin gives a more helical, more toroidal dominated magnetic field. That's why it gives more symmetrical image, more strongly twisted and give more bipolar, so accented bipolar.
Is this measurement possible with GMBA now?
I'm not sure whether detectability of CP component in GMBA, but it's order 1%. If we,
I really, it's just
I think so, yeah. But yeah, I think so. I'm not very familiar with the detectability of CP, but if we have a dynamical range of 10 to the 4, 10 to the 3, the, how say, I believe. Around here is a dynamic range of 1, 10. So 10 here we have 1% of CP. So it's comparable with total intensity in the outermost contour. So we can naively expect we can catch the detect the CP around here. Maybe it's optimistic. Optimism of the theoretician, but anyway. Does anyone have any comment?
Well, we have all the experts here.
So the thing that makes me optimistic, maybe it's not about Stuxnet, but about all of this, right, is that part of the promise of the NGHD is, and I think this is even I'm even more bullish given the GMPA results, is that you will probably have quite good relative astrometry between jet images over time, probably to better than 10 or 5 microseconds, which means that in principle, you can just coherently integrate in bins and even just be twiddle if you want, right? The interferometric beam.
You mean
Forever, right? You can just build.
integrating their
That's right. Your ability to align images over time, you might even be able to use the shadow to do this, right? So that is a very precise astrometric probe. You can just stack all of these, and then you have maps of, I mean, not quite the magnetic field, but things you think you understand in terms of the magnetic field over years, right? And so I actually think it's not crazy to try and dig out these 1% signals from long-term integrations. And I think that the sad thing is that 1% means we're digging into sort of calibration issues, and we're really sensitive to all of the horrors of Stokesy calibration. But at least in linear polarization, I'm very optimistic. You know, this is doable.
Yeah. Actually, I want to bet CP imaging because it's more how to say the most vivid difference between the events.
I remember your Separatrix paper. It's a beautiful, but
yeah, and yeah, it's also nice that we can connect the discussion from the black hole to these extended jet images in the context of bipolar quadrant deep image. We can barely see the how to say quadrant component. How to say the bipolar pattern is also flipped in the equatorial plane, which is light from the frame dragging effect gives the magnetic field and gives a reversing magnetic field polarity, the upside and downside of equatorial. So yeah, we can smoothly discuss on the black hole image to the extended jet image of circular polarization. And finally, I'll talk about non-thermal description and feature prospects. In this work, we have some conservative choice in determining injecting the non-thermal power electron, assuming their energy partition with thermal electrons, and the ratio is 3%. So it's so it's just the non-thermal component is just 3% of thermal in energy. And as a result, as we see in the figure, the power of emission is subordinate to the thermal contribution overall, or over different spins and over different R height. And so as a result, we can we also see the one least brightening feature overall, even with high spinning black hole, it doesn't. So one side is dominant. One side is brightening image. Meanwhile, the actual observation on larger scale, the observation detected double-edged feature in amethyst like this. I will give a talk today. It's you, I think so. Yes. I never. Awesome. It's good. Maybe it's a good introduction, but anyway, starting the injection process. So yeah, we produce this. As a next step, we think of surveying the injection process of non-thermal particles around black hole maybe, yeah. I'm working on this work these days. So we've listened to my talk and leave a summary. Thank you for your attention.
All right, we've run over time, so one burning question. All right, please.
Thank you for the talk. And I actually have a question about you convolve with the beam 40 microseconds, right? But why 40?
I believe it's, I believe there's some the best, how say it? It's something we can expect with global scale with ground-based with global scale with.
So, I mean, maybe if you convolve with smaller beam, then do you expect that you can see more this
more
membranous structure and even like some substructure at the core?
Yes, I can. Every we can detect the substructure. But basically, okay.
Oh, I see. These LP images are also being convolved after time averaging. Is that right?
No, I'll say. Firstly, the image convolved with Gaussian and then averaged.
Oh, sure.
So I think it depends on the models. I feel like the retrograde spin case is more edged, not necessarily one or double one, maybe triple, but yeah, this model shows more edge and blobby emission. So maybe prospective to reproduce the double triple edge.
Okay, thank you.
All right, so of course you is around for further discussions. We'll be having dinner at 5:30 at the Hourly Oyster House, so please let me know before 2 o'clock so I can reserve a table. And let's thank him one more time.
Very clear talk.